We'll start off this chapter on statistical inference by talking about sampling. Say we wanted to know the average height of monkeys in South America. To do that, we'd have to measure the height of every monkey in South America, add them all up and divide by how many are there. Now that's a task, right? That's a really difficult task, probably impossible. So we don't do that. What do? We take just a sample of those monkeys, a smaller subset of the larger population, take a sample of those monkeys and take the average height of that sample. And statistical inference is a set of tools which allows us to make inferences about the population from such a small sample. So we don't have to measure everything in the population, because often that's impossible. Sometimes it's literally impossible, like in the sciences. Say you have some sort of chemical reaction and you need to know what is the average amount of heat that gets released from that chemical reaction. Well, there's no population of those chemical reactions that you can take a measurement of. We've got a theoretical that the chemistry tells us what can happen, but we don't have a population of experiments that we want to take a population of. The population doesn't exist. But by performing a few experiments, we are still taking a sample statistic and then trying to infer what the true value would be, even though there's no actual population there. When we are talking about populations and samples, we have specific language which we use to separate things in population and things in the sample. So first of all, any measurement of a population is called a parameter. So the average height of monkeys in South America is a parameter. If we take in the average height of a sample of those monkeys, we say that that is a statistic. The mean of the population we usually denote with a mu, while the mean of a sample we denote with a x bar. Similarly with standard deviation or variance, the parameter of the population we use sigma or sigma squared for variance, while for the sample we use s. And if we wanted the number of things in the population or the number of things in a sample, we'd use capital N for the parameter and lowercase n for the sample, the number of things in our sample. So yeah, the whole idea behind statistical inference and the set of tools we've got called statistical inference is that we can take a sample statistic instead of the population parameter, and we can ask, what does that sample statistic tell us about the population parameter, that thing that we can't measure? And that population parameter is not necessarily the same as the sample statistic. That depends on the sample you took. Right? You could have taken an extremely small sample or an extremely large sample. But probabilistically, that is going to be unlikely, and we can use that information to make these statistical inferences. There are various methods we can employ in order to do our sampling. The most pure and ideal one is called random sampling. Random sampling is when each observation in the population has the same random chance of being chosen in our sample. Now, this is the most ideal, and all the methods we are going to talk about from now on will assume random sampling. But random sampling is a bit impossible, really. Like, what is randomness for a start? And do we have access to all the population to be able to do this random choice on them? So it's a bit of an ideal. It might be a bit of an unrealistic ideal, but it's a good model for some of the other sampling methods. Similar to random sampling, there's systematic sampling. So now say we want to take the random opinions of people in a shop. In random sampling, we would, every time they go through the door, we'd flip a coin or roll a dice or something, and if it lands on a certain value, they'd be in our sample and we'd ask them a question. With systematic sampling, we'd do something like take every 10th person. If the population itself is sufficiently random, then this behaves the same as random sampling. But if there are some systematic structures in our population, then this might actually introduce some systematic biases. And what that means is that there might be certain observations that we are consistently leaving out of our samples because of the way we are sampling. One way of overcoming that is called stratified sampling. In stratified sampling, we sort of know the makeup of our population and we want our sample to represent that. So for example, if we knew that the city of Cardiff's population is 20% students and we wanted the opinions of Cardiff residents on some new shop, we'd make sure that when we are sending out our questionnaires, 20% of our answers back will come from students, because we know 20% of Cardiff consists of students. Again though, this can have some problems. Say we had a sample of 50 observations and we know that 1% of Cardiff is Egyptian. Do we include an Egyptian person in our sample or not? There's a few things we can do here. We can either just leave them out and that causes some systematic bias, or we can just lump all minorities together, and again that causes some problems too. So there are some problems with this. Similar to stratified sampling, there's quarter sampling. And quarter sampling is the same sort of idea, but instead of saying I want 50% of my observations to be this because that's what the population looks like, it's more targeted towards the task. So for example, if we wanted people's opinion on, say, something to do with LGBT issues, we'd want to make sure that a large proportion of our sample comes from LGBT people, rather than the sort of 4 or 5% of the population that are LGBT. So quarter sampling is similar to stratified sampling, but with a political motivation and good reasoning behind that. Cluster sampling is another type of sampling where instead of sampling one observation at a time, we sample groups of observations at a time. For example, census data, if we had a sample of the census data, we wouldn't have samples of individuals. We'd have samples of households, which consist of more than one individual. So each observation in our sample is actually a cluster of observations together. And there's snowball sampling, and I wanted to include this because I found out about this really recently. So snowball sampling is really interesting. For example, if we wanted to question drug dealers on things. Well, drug dealers are really hard to come by because they tend to keep themselves to themselves. They don't advertise that they're drug dealers because it's illegal. So what we would do, we'd spend a lot of effort finding 1 or 2 drug dealers. We'd give them the questionnaire. And then after they filled in the questionnaire, we'd tell them, now from the drug dealers you know, go and give them this questionnaire. And then they'd fill it in. And then from the drug dealers they know, they'd send them the questionnaire, and so on and so on. We get this snowball effect of the number of observations in our sample, the more iterations we do. Each of these, except for random sampling, each of these has some problems. Each of these can introduce some bias. And bias is okay if we know how to deal with it, or if we acknowledge it. So recognizing bias is really important. Here's a now really famous image which is always used when we talk about sampling biases. So this is President Truman the morning he won the presidency, holding up a newspaper which says that his opponent Dewey defeated him. And why? Well, all the pollsters for weeks and weeks beforehand had said Dewey is going to win a landslide election. So all the newspapers prepared for that, and then Truman won overwhelmingly. What went wrong? Sampling bias. So all the pollsters, they'd rung up as many people in America as they could on the telephone, and they'd ask who you're going to vote for. And most of them said Dewey. Those people weren't lying. There was a problem with their sampling method. This was the 1950s, where only rich people had telephones. And we know now that economic status really influences your politics. And this is called response medium bias. Okay, you have a bias in the medium, the way that you get your responses. Here they use telephones, whereas that meant that only rich people were going to answer them. Some other sampling biases to be aware of: volunteer response bias. So if you're asking for responses from volunteers, you're only going to get a certain type of people responding. Think of Amazon reviews. Amazon reviews tend to be either 5-star reviews or 1-star review. Because if you're like, oh, that was okay purchase, are you going to go and do the effort of volunteering to give it a 3 or 2-star review? No, you're going to be reviewing something if you're really pleased with something or really displeased with something, 5-star or a 1-star. Situational bias is where you might have a bias based on the situation you're in. So if you wanted people's opinion on the food served at a school cafeteria, and you do that by going to the school cafeteria and asking people, then the situation means you're only asking people who are already in the cafeteria. So there's going to be a bias there. Inspection bias. So we've talked about the inspection paradox before, and this is the same thing, super related. There's a really nice example of this, and it's in a book called Orange is the New Black by Piper Kerman. It's now a Netflix series. And in that book, it was about a woman experiencing a woman's prison. And in that book, she noted that there was a much larger than expected amount of people spending really, really long sentences in prison. Most of the people in prison were spending really long sentences, even though, like, most people who get sent to prison get sent small sentences. So what's going on? Well, the inspection paradox is going in here. The people who have long sentences are going to be in prison for longer. So at any point when you go into that prison, a larger proportion of them are going to have longer sentences. All the people with smaller sentences, they're in there for a shorter amount of time, so there's less chance of them being there on the day that you go and ask. And there's survivorship bias. Survivorship bias is a big one. It gets talked about a lot. There's lots of really neat examples of this. Here's an image which sums up survivorship bias, and this story's been told to death by now, but I'll say it quickly. So in World War II, the US Air Force were getting a lot of planes shot down. They were losing a lot of planes. So they thought, all right, we need to go and put extra armour on our planes to make them stronger. So they inspected all the planes that had come back from war. They inspected where had they been shot. And here's a diagram of where the bullets were, shots were in their planes. So there's a lot around that middle area, a lot in the wings, a lot in the tails. So they were going to put extra armour on these areas with lots of bullet holes in. Then a statistician came along and said, no, don't do that. Put the armour on the places where there's not many bullet holes. Why? Because all those bullet holes show is where can a plane be shot and still make it back to become a data point. Then none of the planes came back that got shot in that middle tail area or in the cockpit area. So they are the places that need the extra armour because they are the places that cannot survive being shot. Another example I really, really like is New York City in the 80s. There seemed to be a lot of cats getting injured by falling out of buildings. So some vets recorded some data. They looked at all the cats that came in. They recorded the level of injury they had and how many floors they'd fallen out of. Now what they found was that the larger the fall, the less injuries these cats were having, which seemed really odd. What was going on? If they were falling out of a lower floor, they were getting heavily injured, and if they were falling out of a higher floor, they weren't getting injured at all. So what was going on was the cats falling out of the higher floors were dying, so they didn't make it to the vets. The cats that did make it to the vets that were falling out of higher floors were just the really sturdy cats that could survive falls, whereas all the weaker cats were dying. the weaker cats that were falling out of lower floors were getting a lot of injuries. But because they hadn't died, the vets were seeing those. So the vets weren't seeing all the weaker cats that were falling out of higher floors. So it looked like there was this trend where there wasn't. And that's because of literal survivorship bias, yeah? The cats that didn't survive didn't become data points. And this gets seen a lot. For example, there's lots of anecdotes about people who dropped out of college or didn't do well in school, but they became successful anyway. Jeremy Clarkson does this every time the A-levels come out. He goes, I didn't get any O-levels and I'm still stinking rich. But we only hear from celebrities, right? We only hear from successful people. We don't hear about all the college dropouts who are not successful at all. So all the stories we are getting seem like college dropouts become successful. But that's because we only hear about successful people. We don't hear about the people who are not successful. This also cropped up in a book I was reading recently, and I got so excited when I saw this. It was really interesting. About historical artworks. I was reading an art history book, and they said that most of the paintings we see from like 300-400 years ago seem to be kings and queens or religious pieces. And most people think that 300 years ago people were only painting kings and queens and religious pieces. Whereas that's not true. It's just the paintings of kings and queens and religious pieces were stored in palaces and churches which survive to this day. All the other paintings that people just had up in their houses of like fruit and just streets and cafes and normal people, they got destroyed just like the houses. So they didn't survive to today. So we have this skewed view of the past because of that. And similarly, architecture or anything like that, people always go, oh, they don't build things like they used to. They used to build things to last. But you're only remembering the things that are still around, the things that lasted. You're not remembering all the things that didn't last. So being able to recognize biases like this in your data is really, really important. Again, there's no sort of adjustment we can do, formulas we can plug into our data to get rid of these biases, but it will skew how you interpret some of your data analysis, and being able to do that is really important.